Hello again, welcome back guys. So this is question number 12 of our book, and in this circuit we are given a very simple series configuration of the two resistors in which the source voltage is known, which is the RMS value, and similarly the scope or the oscilloscope is also connected here across this 80 ohm resistor, and from it we have seen that the calculated peak to peak voltage it has is 45.27 volts. So what is the peak to peak voltage? So let us have the voltage waveform across this resistor is basically this one. Okay, so this is the VP while this is the minus VP. Okay, so this VPP is basically this peak to peak voltage, which is this V peak to peak, and we have known it, and this is given here. Okay, as this is a symmetrical waveform, so in order to find the value of Vp from these type of waveforms, what we have to do, we have to divide our peak to peak voltage over 2. Okay, so in the symmetrical waveforms we will get the peak values from this expression, and it will be writing 45.27 divided by 2. We will get how much? 45.27 divided by 2. This will be 22.6 volts. So that is the peak waveform. Just you have to remember that this formula is valid for all the symmetrical waveforms. And what are the symmetrical waveforms? The waveforms where the DC term is this 0 volts, okay, or which originates from the origin and get back to origin. Okay, so this is the symmetrical waveform where the values at the positive cycle are equal to the values in the negative cycle. Okay, so in that case we have this peak waveform. So in that case our peak voltage value is the half of the peak to peak value. Okay, so we have calculated it. After it, you know that this is the peak value here, so we have to find the RMS value from it, because all the calculation here will be done in the form of the RMS or the effective value. So RMS of this value, or let me call it V80. So 80 here is 22.6 divided by square root of 2. Okay, so now calculating it here, what we will have, let me use it, 22.6 divided by the square root of 2. So it will be 15.9, and that is almost equal to the 16 volts. Okay, so here we have this value. Now as we know the value across this resistor as well, and in order to find the value of this resistor, what we can do, we actually have the voltage across this one, and I have earlier told you with every element we have three quantities associated with them. What are basically the current, voltage and impedance. Okay, so if any two of those are known, we can easily find out the third one. Okay, so here we don't have the current, we don't have the voltage, and we don't have the impedance or the resistance here as well. So what we have to do, first of all we have to find out the voltage, and from the voltage we have to find out the current, and after the current we can find out the value of impedance. Okay, so that would be a very lengthy process. As we know the voltage across this 80 ohm resistor, in order to find the value of this resistance here, we can here use a trick in which the value of R will be included and all the other quantities will also be included. So we can use here the voltage divider law at this resistor. Okay, so in order to find the value of V80, we have the voltage divider law, in which the value of the resistor across, we want to find out the voltage is known, and also the summation of all the resistors which are connected in series multiplied by the total voltage. Okay. So, that is known here. Do we know the value of VAT? Yes, we also have the value of VAT, and that is 16. So, 16 is equal to the 80 multiplied by 20 divided by R plus 80, or that is 16 R plus 80 is equal to the 1600. Okay. Now, in order to find the value of R, let me simplify it, and it will be R equal to the 1600 divided by 16 and here minus 80. So, this will be cancelled out, and here 100 will be left out, and here R will be equal to the 100 minus 80. So, the value of R will be equal to the 20 ohm. Okay. So, that is the value of the resistance which we had to find here. Okay. And this is the method which we have used, and a very convenient and a very shrewd trick which we have used here in order to find out this value. So, this is basically the concept that how you can use other methods in order to find the quantities by using the concept of the other techniques which we have so far seen. Okay. So, thank you so much, and I will see you with some more tips, more tricks, and more solutions of the circuits like this one in our upcoming video. Thank you so much. Welcome back, guys. So, this is question number 13 of our book Introductory Circuit Analysis by Robert Boylestad, and here we are given this circuit in which we have this digital multimeter readings for the current and for the peak to peak voltage as well. With this peak to peak voltage is basically calculated from the oscilloscope, okay, while this one is calculated via digital multimeter. Okay. So, from it what we have to calculate, we have to determine the value of L, which is this one, and also the value of this resistance as well. Okay. So, let us proceed here. So, part A of our question, we have to find out the value of L, and we know very well that to find L, let me have the expression for V of L, and for V of L I know that V of L is I x of L. Okay. This is equation A, and also from x of L we know that x of L is omega L. Okay. This is equation B, and here omega is equal to the 2 pi f. This is equation C. Okay. So, now in order to proceed here, let me first find my quantities here. So, this one, the total voltage here or the source voltage here is basically in RMS, the current is in RMS, while the value of the voltage here is basically the peak to peak voltage. Okay. So, I have recently covered that how this peak to peak voltage seems like. So, let me have it, this V peak to peak, and that is 21.28 volts. So, now in order to find the Vp in the symmetrical waveform, what we have to do, we have to 21.28 divide it over this 2. So, what I will get here, let me use the calculator here. So, here 21.28 divided by 2. So, it will be 10.64. So, this is 10.64 volts, while this one is the peak voltage. I know previously that Vrms is equal to the Vp divided by square root of 2. So, let me use the same procedure here. So, 10.64 divided by square root of 2, how much would it be? So, dividing it over square root of 2, I will get 7.5 volts. Okay. So, writing it here 7.5 volts. This is the RMS value of V of L. So this is V of L. Okay, so I know the value of V of L. I have the value of current here, which is same here, because this is a series circuit which is consist of these two elements. So this equation satisfies, but how to find the value of omega? So let me start it from C here. So let me write values here. So 2 pi, and the value of f is also given here, that is the source frequency, and that is 1000 hertz. Okay, so writing it, 1000 multiplied by 2 is 2000, 2000 multiplied by pi is how much? 2000 multiplied by 3.14, and that would be 6280. So that is 6280 radians per second. Okay, now taking it from here, okay, and putting it here. Okay, when I will put it here, what I will get here? I will get here the value of x of L will be 6280 multiplied by L. Okay, so this is the expression for x of L. Now taking this one, okay, and putting it over here. Okay, so now let me use it. Okay, so V of L is I x of L. Putting the value of x of L, what I will get? VL is equal to the I multiplied by 6280 multiplied by L. Okay, or the value of L here is how much? L is VL divided by I into 6280. Do I know the value of V of L? Yes, it is known, and that is 7.5. Do I know the value of I? Yes, this is also known, and this is the 29.94 milliamperes. So 29.94 milliamps, which is 10 to the power minus 3, and that is here 6280. Okay, so now let me simplify it. So 7.5 divided by how much? So let me use this expression as a denominator of this equation. So 6280 multiplied by 29.94. okay, so this would be this one, and dividing it over 1000, because this is 10 to the power minus 3. So how much it would be? It would be 188. Okay, this is almost 188. Okay, so now simplifying this one again. So 7.5 divided by 188, this is 0.0398, 0.0399. okay, so this is the value of the inductor, or if you want to find it in the millihenry, so in millihenry it would be 39.9 millihenry. So that is the value of the inductance which we had to find out. Okay, so through this procedure we have found out all these values. Okay, so that is the part A of our question. So in order to proceed, what we have to find out, we also have to find out the value of resistance here as well. So now to find out the value of this resistance here, what we have to do, we know that with every element we have three quantities associated. What are those quantities? The current, the resistance or impedance, or the voltage. Okay, so these are the three quantities. I have previously stated that if any of the two quantities are known, we can very easily find out the third quantity as well. Okay, so we know the current here, but we don't know the voltage here. Okay, so let me first find the voltage here in part B. So in our question here, we can very easily see that here the phasor sum of total voltage voltages across elements is equal to the source voltage. Okay. Here we have these two elements, inductor, resistor, and then this source voltage here. So, the phasor sum of the voltage which is consumed across this resistor and the inductor here is equal to the source voltage. Okay. So, how to use this equation here? So, now here we can see that E is equal to the phasor sum of VR and VL. Okay. So, this is basically the phasor sum. Why am I using the phasor terminology or phasor summation over and over again? Because here we can see that resistor is basically the real quantity, and in resistor we have this will be the voltage. Okay, because no phase shift can occur, but when we consider this V of L, we will see that V of L is equal to the I j x of L, which is I multiplied by x of L with an angle of 90 degrees. Okay. So, this j is basically corresponds to this 90 degrees, therefore, it will lie here at positive axis. So, it will be x of L and it will make this angle here. So, these are basically the quantities, and to find the value of E, what would we found out here? We will see that it will be somehow like this. This is V of L. So, now in order to find it out, let me plot their values. So, here this will be VR. Okay. This will be VL and the source voltage will be here. So, this is here. Okay. So, here what we have to find out? We have to find out the value of V of R. So, therefore, in this, let me use the Pythagorean theorem. So, according to that, E is equal to the VR square plus VL square. So, that is equal to E square. So, now in order to find the value of VR, VR will be equal to the E square minus VL square whole square root. So, let me use these values here. Do I know the value of E? Yes, it is also known, and it is 10 volts. So, 10 square minus what is the value of V of L? So, the value of VL is also known, and that is 7.5. 7.5 whole square root. Okay. So, let me use calculator here. So, 10 square minus 7.5 square, it will be 43.75, and square root of 43.75. So, let me 43.75, this is V of R, or the value of V of R will be equal to how much? Square root of 43.75, it will be 6.61. So, this is 6.6 volt. So, the value of VR is 6.6. Okay. Now, to find the value of resistor here, let me use the Ohm's law. So, V of R is equal to the I multiplied by R, or the value of resistance is VR divided by I. I know the value of V of R, that is 6.6, and the value of current is how much? It is already mentioned here, and that is 29.94 milliamps. 29.94 into 10 to the power minus 3. So, it will be 6.6 divided by 29.94 into 10 to the power 3. Okay. So, let me calculate it. 6.6 divided by 29.94. So it would be 0.220. So 0.220 to 10 power 3, or ultimately I will get here 220 ohm, because this is 1000 multiplied by 0.220 is 220 ohm. Okay, so that is the value of resistance. So in this question we have found out how to use the values calculated from the oscilloscope and digital multimeter to find the values of the unknown quantities which are available in our circuit. Okay, this is somehow like a practical example in which in many scenarios, in many circuits, we don't know the internal configuration of any circuit, or inside the black box we don't know the quantities available. So at the output of our system we can connect the oscilloscope, digital multimeters, and can very easily find out the internal configuration of our circuit. Okay, so that's it for today, and with some more interesting questions I will see you in our upcoming video. Thank you so much. See you soon. Hello again, guys. So another very interesting question in which we are given the reading of the oscilloscope to find the unknown quantity here, and that is the value of the capacitance which is inside the black box, and we just have the value of the peak to peak voltage across this resistor. Okay, so how to use these values here? So let me first convert this peak to peak voltage into the RMS value. So in order to do it, let me use this V of R is equal to the 8.27 divided by 2. Okay, so it would be the peak value, because this is a peak to peak value, and at the end I have to divide it over this square root of 2. So I will get here 827. Okay, 8.27 divided by 2 into square root of 2. Okay, so why to use this square root of 2? Because I have previously mentioned that Vrms is equal to the V peak divided by square root of 2, and using this similar concepts here, and similarly Vp is equal to the V peak to peak divided by 2. Okay, first putting it here, and then using this mechanism to find the values, the ultimate numerical values will be here. Okay, so I have also mentioned all these concepts in our previous videos. So now simplifying it, I will get 8.27 divided by 2. So it is 4.135 divided by square root of 2, 2.92. Okay, so that is basically 2.92 volts, and that is V of R. Okay, as I already know the value of VR now, so by using the voltage divider law in this circuit, I can see that V of R is equal to R divided by R plus X of L multiplied by what? Multiplied by the source voltage, and that is E. Okay, now putting their values here, what I will get, this will now, or rearranging it to find the value of X of L, what I will get, V of R, R plus X of L equal to R multiplied by E, or VR multiplied by R plus VR multiplied by X of L is equal to R multiplied by E, or to find the value of X of L, subtracting VR multiplied by R in both sides, what I will get, VR into X of L is equal to R multiplied by E minus VR multiplied by R, or from here I can also see that it will be R E minus V of R whole divided by V of R, and that is equal to the X of L. Now putting values here in this equation, so let me call it equation A. Putting values here, what I will get, the value of R is given, and that is 10 kilo ohm. That is 10 into 10 to the power 3 for the simplicity. What is the value of E? E is also known, and that is 12 volts. 12 minus what is the value of V of R, the voltage which has been detected across this resistor. So, that is already known, that is 2.92, okay, whole divided by V of R. So, whole divided by V of R is 2.92. Okay. So, now let me simplify it. So, for simplifying it, let me first 12 minus 2.92. Okay. So, it will be this one 9.08 and 9.10 to the power 4 into 9.08 divided by 2.92, or divided by 2.92, this is 3.10, and 10 to the power 3 multiplied by 10 into 3.10, or it will be 31 into 10 to the power 3, or ultimately it will be 31 kilo ohm. Okay. So, that is the value of X of L which I had to find out here. Okay. So, from our previous expressions, I know that the value of that is X of C. Let me now use X of C here instead of this X of L, because this is the capacitor. So, X of C is 31 kilo ohm. As I know that X of C is 1 over omega C, or the value of C is 1 over X of C multiplied by omega. Now, let me put their values. So, X of C is how much? That is 31 into 10 to the power 3. Okay. What is the value of omega? That is 2 pi into F. Okay. So, it will be 31 into 10 to the power 3 into 2 pi into what is F here. So, F is 40 kilohertz, 40 into 10 to the power 3. So, here it will be capacitance will be here, and that would be, let me move this 10 to the power 3, 10 to the power 3 is 10 to the power 6. So, 10 to the power minus 6 in the numerator, and here 31 into 2 pi into 40 is how much? 80 pi. Okay. So, now let me calculate it. 31 into 80 into 3.14, it will be like here, and taking reciprocal of it, what I will get? So, reciprocal of it will be this one. So, this is 1.28 into 10 to the power minus 4. So, 1.28 into 10 to the power minus 4 into 10 to the power minus 6. So, it will be how much? 1.28 into 10 to the power minus 10 farad. Okay. So, that is the value here, and in order to convert it into the nanofarad, what I can do here? Now, let me use here 0.128 into 10 to the power minus 9 farad. Okay. So, ultimately I will get here 0.128 nanofarad. So, that is the value of the capacitance or the capacitor which I had to find out. So, that is it for today, in which we have found out the value of the capacitor in this question. So, I will see you with some more question in our upcoming videos. Thank you so much. Hello guys. So, today we are going to discuss the voltage divider law, in our AC circuits. So if you recall, we have discussed the same rule or law in our DC circuits. So what was basically the voltage divider law? So suppose we have a voltage source here, and with this we have different impedances connected in series, okay, just like this one and this one here as well, okay. So if we have these impedances connected, so let me call it Z1 and this is Z2, and this is, let me call it E, or the source voltage, okay. So let me have the voltage drop across Z1 is V1, and similarly let me represent it with the red color. This is V1, okay, and across Z2 I have V2, okay. So now in order to find the value of V1, V2, what we have to do, first of all we have to calculate the current, and after calculating the current we have to find the V1 and V2 by using Ohm's law, okay. So we are again at the mercy of the current. So in order to remove the dependency upon the current, what is here, we have the voltage divider law, and in order to find the voltage divider law, what we have to do here, in order to find the value of V1, what we have to do, we have to write the impedance across which we have to find the voltage and divide it over the equivalent resistance, which is in this case, basically in this series case, is the summation of all the resistances which are connected in series, okay. And at the end we have to multiply it with the source voltage. So that is the voltage divider law, and through which we can calculate V1, V2, V3, whatever we want to calculate. So if this is V1, so V2 can be calculated by V2 is, so now V2 is across Z2. So in numerator we will have Z2, and as the equivalent resistance will remain same here, so therefore it will be Z1 plus Z2 here, which will be multiplied with this total voltage, okay. So now here we can see that in our part A of question 15 we have to calculate the values of V1 and V2 with the given source voltage and the given resistance is here, or the given impedance is here, okay. So what we have to do, so here this is the same circuit here, while the value of Z1 here is 2 kilo ohm, while the value of the Z2 is 8 kilo ohm, okay, while this is R, while this is X of L, okay, because this is the inductor, so that is the inductive reactance, while the value of the source voltage is 120 volts and the angle it has is 60 degrees. So now let me put values here in order to find the value of V1. So what will be the value of Z1? So Z1 is 2 kilo ohm, which is already known, okay, that is 2 kilo ohm divided by Z1 is again 2 kilo or 2000, and plus I have to write the value of X of L. But wait a minute, this is the inductive reactance, and inductive reactance cannot be directly added with the linear resistance. So what we have to do, I have to use this J here, and this is now 8 kilo ohm, which is 8000 multiplied by the value of the source voltage, that is 120 with an angle of 60 degrees. Okay. So now here we can see that all the operations here are either multiplication or division. So the feasible form here will be the polar form. Okay. So now I have to convert them into the polar form, and in order to convert them into polar form, let me convert first this one into polar form. So as this is a linear element or the resistance, so this is 2000 and the angle it has is 0 degrees multiplied by 120 this one, and the angle it has, this is already in the polar form, it is 60 degrees divided by the 2000 plus j 8000. Okay, so that is the rectangular form. Let me convert it into the polar form. So 2000 plus 8000, okay, with the iota here. Okay, so now I have this number, and in order to convert it into the polar form, let me use this one. So it will be 8246 8246 point how much, 21 or 2, okay, and the angle it has is how much, angle is 75.96 degrees. Okay, so now I have this term here, so the value of V1 will be how much, so V1 will be 2000 multiplied by 120 whole divided by 8246.2, okay, and the angles, these two are multiplying together, so therefore 0 degrees plus 60 degrees, while this is in the denominator, so therefore it will be subtracted from it, so I will have 75.96 degrees. Okay, so now let me find it. So V1 will be equal to how much, 2000 multiplied by 120, so that is 2,40,000 divided by 8246.2. okay, so that is now 29.10 volts with an angle of, this is 60 minus 75 is minus 15.96 degrees. So this is the value of V1 or the voltage which is dropped here, or the voltage here which is now across 2 kilo ohm resistor. Okay, similarly, in order to find the value of V2 here, I have to use Z2 divided by Z1 plus Z2 multiplied by E. Okay, now putting their values, the value of Z2 is how much, this is now the Z2 which is X of L. So as this is the inductive reactance, so therefore it will be J 8000 divided by Z1 is again the same value it has, and that is 2000 plus J 8000 and multiplied by the 120 with the 60 degrees here. Okay, so now let me simplify it some more. Okay, so this J 8000 again in the polar form will be 8000 with an angle of 90 degrees multiplied by 120 with an angle of 60 degrees. Okay, so while this one is here same as that of the previous one, and previously we have calculated the polar form of it, and that was 8246.2 with an angle of 75.96 degrees. Okay, so now let me simplify it. So 8000 multiplied by 120 whole divided by 8246.2, while the angle it has will be 90 degrees plus 60 degrees, while this one, the denominator term, will be minus 75.96 degrees. Okay, so now let me calculate it, and calculating it I will get it here. So 8000 multiplied by 120, this is this one divided by 8246.2. okay, so how much it would be, it is 116.4, so 106, and the angle it will have will be 90 plus 60 minus 75.96, so it will be how much, this is now 74.04. okay, so the angle I have is basically the 74 point how much, 04. So that is the voltage which is basically the V2. So in this question we have found out the voltages which are here. So by using the voltage divider law, we have developed a mathematical formulation here, and after that mathematical formulation we have found our values. Okay, so this is part B, and we will solve it in our next video. So you are supposed to try these things by yourself and see whether the results are correct or not. Okay, so thank you so much, and I will see you with some more question in our upcoming video. Welcome back, guys. So today we are going to start part B of our question 15. So what is in part B? So here again we are going to find the value of V1 and V2 by using the voltage divider rule. Okay, so again following the same procedure here, but first of all let me calculate the total impedance. Okay, so the only difference between the previous circuit and this circuit is that previously we had two impedances. The first one was the resistor while the second one was the inductor, while here we have three impedances, and from these three we have to find the voltages across two of them. Okay, so what do we have to do? Many students find it difficult to calculate the voltages across the subset of the elements if more than the desired number of voltages impedances are available. Okay, so here we want to find out Z of t. So Z of t is what? So here we have this resistance, this impedance, and this impedance as well. So let me calculate them. So 6.8, okay, plus J40, which is for this inductive reactance, okay, and similarly this 22. Now calculating it, what I will get, Z of t will be equal to 6.8 plus 22, real was with real, and plus J40. Okay, what will we get here? So ultimately total impedance will be 6.8 plus 22 is 28.8, and this is plus J40. So this is the impedance in rectangular form. What we have to do, let me change it to the polar form as well, because we may need it. So that Z of t is 28.8 plus 40 with the iota here. So where this one, okay, or this one here. Okay, now converting it into the polar form, let me press shift and then this, and now 3. So it will be what? 49.28, 49.3, okay, and that is the ohm, while the phase angle associated with it is 54.25, 54.25 degrees. Okay, so that is the total impedance. Now what we have to do, let me represent this one with V1. We want to calculate this V1 and also this V2. Okay, so now let me calculate them here. So we know that according to the law, V1 is equal to, that is V1, and that is equal to this 40 ohm inductive reactance. So here it would be JXL or J40 divided by the total impedance, which is already calculated here. So that would be 49.3 with an angle of 54.25 degrees, okay, and multiplied with the total voltage, which is this one here, that is E equal to 60 volt with the 5 degree here. So 60 with the 5 degree. Okay, so now all the terms here, I can see that the operations involved here are basically the division and multiplication. So all the terms should be in polar form in order to calculate all the required quantities in a very simplified or easy manner. Okay, so therefore this one is basically in the rectangular form. So let me convert it into the polar form. When it will be converted into polar forms, J will be removed here and it would be here 90 degrees. Okay, because I have previously explained in the video, which I will again put link over here. So it will show you that when you will remove J from here, you will have to use the angle of 90 degree. Okay, so now let me calculate the value of V1. So value of V1 will be 40 multiplied by 60 divided by 49.3. These are all the magnitudes of all the phasors. Similarly, the angles here are 90 degree, which are all the numerators. So, plus 5 degree, these are the numerators here, while the denominator term will be subtracted from here. Okay. So, now let me calculate them. So, 40 multiplied by 60, so that is 2400 divided by 49.3. So, it would be how much? That is 48.68. Okay. And as this is in volts, so let me write volt here. And now, in order to calculate the angles, so what I have to do, let me write here 90 plus 5 minus 54.25. Okay. So, that would be how much? It would be 40.75. 40.75 degrees. So, that is the value of V1. Okay. Similarly, now in order to find the value of V2, let me use the green color here, and that is V2, and the concerned value of the resistor across which I want to find out the voltage. So, that is 22 divided by the total impedance. Okay. So, 22 ohm divided by the total impedance, which is 49.3 with the angle of 54.25 degrees, and multiplied by the total voltage, and the total voltage applied across it is 60 with an angle of 5 degrees. Okay. So, here V2 will be equal to, as this is a resistor, so resistor is basically the linear term. So, the angle associated with it will be 0 degrees. Okay. So, here it would be 22 multiplied by 60 divided by 49.3, it would be, and here the angles will be 0 plus 5 degree, because both are here in the numerator, and the denominator term will be subtracted here. So, 54.25 degrees. Okay. So, now let me calculate it. Okay. So, 22 multiplied by 60, that is 1320 divided by 49.3, and it would be 26.77 volts with an angle of, here let me use it. So, 0 plus 5 is 5, 5 minus 54.25 is minus 49.25 degrees. Okay. So, that is the value of what? That is the value of V2. Okay. So, that is it for today, in which we have calculated the values of V1 and V2 in part B of our question. Here the sole difference between the circuits is that here we are having these 3 resistors, but what I want to find out? I want to find out the voltages across the other 2 resistors. So, students usually make it very difficult to find the values here, because they see that these are the 2 resistors. Okay. So, they usually find the impedance or the total impedance, which is the combination of J40 plus 22. Okay. But that basically is not the total impedance. Total impedance also consists of this one. Okay. So, that is why I first of all calculated the value of Z of t, which is basically composed of 6.8, J40 and then 22. Okay. So, that is the essence of this question, in which I have solved the mystery of these type of circuits. Okay. So, that is it for today, and I will see you with some more interesting questions in our upcoming video. Thank you so much and see you soon. Welcome back, guys. This is question number 18, and here we are asked that an electrical load has a power factor of 0.8 lagging. Okay. So, it dissipates 8 kilowatt at a voltage of 200 volts. Calculate the impedance of this load in rectangular coordinates. Okay. So, that is a very interesting question, and let me depict it by using a figure. So, let me have a figure here in which we have this load. Okay, so what is basically the applied voltage here? The applied voltage here is, let me have it, 200 volts, and the power which dissipates across this load is 8 kilowatts. Okay, and the power factor associated with this load is 0.8 lagging. What we have to find out? We have to find out this Z naught. Let me call it Z naught. I have to find out this Z naught, and first of all let me also find out the current which it is getting out of this source. So in order to find it out, what are the quantities? I have this power factor here, so I know that the power factor is equal to the cos of theta. Okay, or in order to have it, I can also see that cos of theta is 0.8, or in order to find the value of theta, what is equal to cos inverse of 0.8, and what is it equal to? Let me calculate it. So cos inverse of 0.8, how much would it be? That is 36.87. so theta is 36.87 degrees. Okay, so that is the theta which I have. So now what else do I have? I have this power as well, that is the power dissipated, and that is basically the real power. So I know that the power is, real power is always equal to P equal to IV cos of theta, where this cos of theta is the power factor. Okay, which I already know. So all the quantities here are known except this current. So in order to find the current here, what it will be? So it would be P divided by V cos of theta, or putting values here, what I will get? It would be 8000 divided by V, that is 200 multiplied by 0.8. Okay, so these two will cancel out, and here this will be 40. So 40 divided by 0.8. So let me calculate it. 40 divided by 0.8, and how much it would be? This is now 50 amperes. Okay, so the current, magnitude of the current is already known, which I have calculated right now. So now as the magnitude is already known, but there is another term here which is this lagging. Okay, and I have previously told you, whenever this lagging term is used, that it will always be associated with the current. Okay, always the current when leads, when this is leading, it means the current is leading. When the power factor is lagging, it means current is lagging. So here in power factor calculation, or in here always, there is always a relationship between voltage and current. Okay, so now here, as voltage is leading and current is lagging, therefore in polar form, what it would be? It would be, if this is 200 and the angle with it is 0 degrees, so here this current would be how much? The magnitude it has is 50, while the angle it will have is this 36.87, which I have obtained from my power factor, and it would now be minus 38.87 degrees. Okay, because of its lagging nature. And on the phasor diagram, you will very easily see that if this is the voltage which is now leading, so the current here will be here, which is lagging, and the angle it is making with it is theta, and this is what? This is the current. So that is the phasor diagram, and here this relationship is valid. Okay, so from it I have calculated all the values. Okay, so that is now a very simple circuit where I know the current, I know the voltage, and I want to find out this Z naught. So here the validity of Ohm's law also applies here. So according to Ohm's law, V is equal to I Z naught, or the value of Z naught is how much? That is V divided by I. Okay, so now let me put these values. So Z naught is 200 0 degrees divided by the 50 with what? Minus 36.87 degrees. Okay, so that would be how much? That is now 4, and 4 ohm with an angle of 36.87 degrees. So that is the impedance of my load. But as we are asked to find out it in the rectangular form, because in that manner I would clearly know that what is the actual resistance and what are the reactive elements available in my load. So let me first do it in what? In my form here. So that is now 4, and the angle associated with it is 36.87. Okay, so that is here, and the that is now the direct form, because now that is complex and I already selected it to convert it into the rectangular form. So it would be 3.19. okay, so let me write it. So Z naught is now 3.19. okay, and with it the, yes, this is plus j 2.4, what? 2.4, yes, that is 2.4. So that is the impedance, where this is the real term which shows the resistance, while this is the reactance of my load. So due to this reactance, the power factor is now lower than 1, and that is now 0.8. okay, so that is a very interesting question, by using which I can find out the impedances which are already connected with the machines, or in any household or anywhere, whatever I want to find out. Okay, so that's it for today, in which I have calculated the value of current, and from it I can also find out very useful information, just like the power consumption, energy consumptions, and so on. So that's it for today, and I will see you with some more interesting questions like this one in our upcoming videos. Welcome back, guys. So question number 20 of our book, in which we are asked to find the series element or elements that must be in the enclosed container, which is here. So that is basically the enclosed container to satisfy the following conditions. Okay, so conditions are basically mentioned here as part A and B. So in first condition here is that the average power to the circuit is 300 watt. Okay, and in second part we are told that the circuit has a lagging power factor. Okay, so here, in order to approach this type of question, what we have to do, first of all, let me calculate this theta. Okay, because theta is one of the very important terms here in order to find the nature of the power factor. Okay, so initially what we have given here, we are given the current, we are given the total voltage, and the resistor which is in series with this impedance, let me call it Z of X. Okay, so we have to find out Z of X according to our conditions which are mentioned here. Okay, so here the average power of a circuit is also given, that is 300 watt. So I know that P is equal to the IV cos of theta. Okay, where this cos of theta, okay, this term here is the power factor. Okay, so we have to find it out. So in order to find it out, what we have to do, let me calculate this cos of theta, and cos of theta is P divided by IV. Okay, let me put their values here. So P is the required average power is 300 watt. Okay, divided by the value of voltage, which is 120. Okay, and the value of current is 3. So that is now 300 divided by 360. Okay, and it would be equal to, let me calculate it. So 300 divided by 360 is how much? That is 5 by 6 or 0.83. So that is now 0.83. So that is the value of cos of theta. The cos of theta is equal to 0.83, okay, and the value of theta from this expression is cos inverse of 0.83, okay. So let me calculate it again here. So cos inverse of this is 0.83, that is how much? So this is basically 33.9 degrees. 33.9 degrees, and that is this theta, okay. So the value of theta is 33.9, while according to this condition that the circuit has a lagging power factor, the power factor is already known, and that is 0.83, while when it will be lagging, so we will see that the voltage will lead while the current will be in lagging situation. So therefore I here will have the value 3 amperes, and the angle associated with it will be minus 33.9 degree, because of the same reason which I have mentioned in our previous video, okay. So that is the value of current. Now in order to find out the value of this impedance, what I have to do, I have all the required values which should be here in order to find the total impedance, because the total voltage is known, total current is known. So I can very easily find out the total impedance from this circuit as well. So therefore I have to make this circuit like here, this is the voltage source, while this one is the total impedance, and inside of it I have this resistor and this Z of X as well, okay. So that is now 2 ohm, okay, and the total overall impedance here is Z naught, which is basically 2 plus Z of X, okay. So why am I transforming this circuit into this one? Because the current which is given here is the total current, okay, that is the total current which this circuit is now getting, okay, and that is also the total voltage which has been applied across the total impedance, okay. So therefore we cannot separate out this 2 ohm resistor from the overall impedance. So therefore I want to find out the total impedance here, Z naught, okay. So in order to find the Z naught by using the Ohm's law, this point will be somehow clear now again, because according to the Ohm's law, E is equal to I Z naught, okay, or the value of Z naught, which is the total impedance connected with this voltage source, is A divided by I, okay. Let me put their values here. So it would be 120 degrees divided by the value of current is 3, and the angle with it is minus 33.9, okay. So this Z naught will be equal to the 40 ohm and 0 plus 33.9 degrees, which will ultimately give me Z naught equal to the 40 ohm with an angle of 33.9 degrees. So that is the total impedance which we can see from this transformed version here as well. So that is, this is basically the total impedance which is Z naught, okay. So let me convert into the rectangular form, because from here what I have to find out, the actual thing which I have to find out here is this Z of X. So here converting it into the rectangular form, let me use calculator here. So 40 and with an angle of 33.9, how much would it be? So that is 33.2, okay, 33.2 and 22.3, 33.2 plus J 22.3. So that is the Z naught. So what this Z naught is equal to, I have previously told you guys that this z naught is also equal to the 2 plus zx. Okay, so z naught is equal to 2 plus z of x, and the quantity which I want to find out here is this zx, which is now z naught minus 2. So let me put these values here. So zx is now 33.2 minus 2 plus j 22.3, or z of x is equal to, this will be 31.2 plus j 22.3. okay, so that is the required impedance. Okay, so now we can see that our whole circuit will be like this one. This is the resistance of 2 ohm, okay, which I had previously, and that is basically the voltage source, which is of 120 volts with a 0 degrees, and the current is of 3 amps and minus 33.9 degrees. Yes, 33.9 degrees. Okay, so this was basically here. What was here? We had this black box, and inside of it we had to find out the value of z of x. So now we can very clearly see here that the value of zx here is 31.2 plus j 22.3. So this basically 31.2 is the value of the resistor, while this 22.3 is the imaginary term. So therefore it basically shows us the reactive element, as the value of j here is positive. So that's why this one is the inductive reactance. Okay, so this is the whole impedance which will be inside this box. So therefore I can draw it like the first element here is this resistor, while the second element will be in series with it, and that is the inductor. Okay, so that is x of L, and that is now 22.3 ohm. Okay, while this is the resistor, and that is 31.2 ohm. Okay, so that is the end of our question, in which we have obtained this impedance from the conditions which are mentioned in our question here. Okay, that's it for today, and I will see you with some more interesting questions in our upcoming videos. Thank you so much, and I will see you soon. Welcome back, guys. So today we are going to learn another very important technique, and that is the current divider rule. Okay, so current divider rule is one of the most important rule in the circuit analysis. Okay, which is used to find the unknown currents. Okay, so in order to learn all the concepts behind the current divider rule, we are going to solve the question number 34 in our book, in which we are asked to find the values of current I1 and I2, okay, in a circuit where the total current or the source current has been given. So in order to solve this question, let me represent I1 with the red color, while this I2 with this green color. Okay, what we have to do, we have to apply the current divider rule to find out the currents here. So in order to do it, let me represent my circuit with another circuit, in which the impedances are represented by these blocks. Okay, so this is block number 1, and similarly here we have another block, and let me call the impedance of it is Z2. Okay, so this is Z2, this is Z1, and what we have to do, we have to find out the current I1. I am representing it with the red color as I have mentioned it here, and similarly I want to find out the current I2. Okay, which I am going to solve by using the green color. So in order to find the value of I1, what I have to do, so by current divider law or current divider rule, what I have to do, I have to find out the value of current I1. So I have to take the ratio of the impedance which is in parallel with the impedance across which I want to find out the current. So the impedance across which I want to find the current here is the Z1, and the parallel impedance with it is Z2. Okay, so what I have to do for I1, I have to write here Z2, okay, and divide it over the summation of the impedances which are connected in parallel with each other. Okay, so here Z1 and Z2 are connected in parallel, so I am taking their summation and multiply it over the current, which is basically the source current, which is here. Okay, so that is the source current, and I have to multiply it with this one. Okay, so this is a very interesting equation, and that's why this is called the current divider rule. So here I have an issue that in this circuit I don't know the values of Z1 and Z2, while here I can find out the values by using the ratio of Z2 over Z1 plus Z2, while the value of I is already known, which is here. This is the value of I, which is already known. So in order to find the values of Z1 and Z2, let me see it here, that here we can see that this is Z1. Okay, if I can see here that, okay, so let me draw these values over here. So this is now, if I can see, so this is now Z2, while this one here, this is Z1. Okay, so here I can very easily see that the value of Z1 is how much, that is 22 ohm. As this is a real quantity, so I am going to write it like this one. Okay, similarly the value of Z2, we can see here that here two inductive reactances are connected in series with each other. So in series the impedances are added together, so I am going to write Z2 as XL1 plus XL2. Okay, so as these are the inductive reactances, therefore I must have to write J with them here as well. Now writing their values, what I will get, this will be J, the value of XL1 is 60 and the value of X2 is 20. So here Z2 will be equal to how much, this is now J 80. Okay, so that is J 80 ohm. So now I know the values here, so let me put these values over here. So I1 is now equal to the value of Z2 is J 80 divided by Z1 is 22 plus J 80 and multiply it with this current, total current, which is already given here, and that is 20 with an angle of 40 degrees. Okay, so now this one is the equation here which I have to solve, and for solving them, it is already known that here the mathematical operations involved are basically the multiplication and division, and for the multiplication and division the most feasible form for us is the polar form. Okay, so now I will also put the link of the video over here if you want to revise the concepts of the phasor. So I am putting the link over here. So now in order to solve it, what I have to do, converting them into the polar form. So here this J80 will be 80 with the 90 degrees. Okay, while this A22 plus J80 is how much, so let me calculate it. Okay, so 22 plus 80 with the iota. Okay, now converting it to the polar form, this one, and in polar form it would be 82.96. okay, so that is now 82.96, and the angle it has is how much, angle is now here, so that is 74.62. 74.62 multiplied with the current, which is already in the polar form. So now let me solve it. So here I1 is here, so now writing the amplitudes here. So 80 multiplied by 20 divided by 82.96. okay, and the angles associated with them are 90 degrees plus 40 degrees. So these are basically the angles associated with the numerators, while the denominator angle will be subtracted from them. So it would be 74.62. okay. So now the value of I1 is how much? Let me calculate it. So 80 multiplied by 20 divided by 82.96. so it would be how much? That is 19.29. so 19.29 amperes. okay, and the angle it has is 90 plus 40 is 130. 130 minus 74.62. so 130 minus 74.62, how much would it be? It is now 55.38 degrees. okay, so that is the value of current which I had to find out here. So I have very easily find out the value of current I1 by using the current divider law here. okay, now in order to find the value of the current I2, let me use the green marker here. So in order to do it, what I have to do, let me write the formula for the current divider law. So I2 is now how much? So the I2 current is flowing through the impedance Z2. so therefore I have to take the value of Z1 which is in parallel with the Z2. so Z1 then divided over the summation of the impedances and multiply it with the total current. So the same values here. Now writing the values here. So the value of Z1 is how much? The value of Z1 is, we can see here that this is 22 ohm. So 22 and divided over Z1 plus Z2, which is already the same value. So I have already converted it into the polar form. So let me use the polar form here as well, and that is 82.96 with an angle of 74.62 and multiply it with the total current, which is 20 and 40 degrees. okay, so this one is again here. So now let me calculate the value of I2 by using the same procedure which I have done previously. So this 22 is the real quantity, therefore the angle with it is now 0 degrees. okay, so now multiplying the amplitudes. So 20 multiplied by 22 divided by 82.96. okay, and the angles with it are 0 plus 40 and minus 82.96 degrees. okay, so let me calculate it. So I2 is how much? Let me calculate it. So it would be 22 multiplied by 20 divided by 82.96. so it would be how much? That is 5.3 amps. So this is now 5.3 amps, and the angle it has is, that is plus 40 and minus 82.96 is minus 42.96 degrees. okay, so that is the value of current which I had to find out. So this is I2. So we have seen that by using the current divider law we have found out the values of I1 and I2, and you can also find the same values if you already know the input current, which is basically the source current, and all the impedances which are connected in parallel with each other. okay, so that is the essence of this question, and I hope all the conceptual ambiguities are cleared now. okay, so thank you so much, and I will see you with some more questions in our upcoming videos. See you soon. Welcome back, guys. So this is now another question. This is basically the part B of question 34, in which again we are asked to find out the values of current I1 and I2, and here we can see that the total current is already known. okay, so what we have to do, we have to apply the current divider rule which we had previously used. okay, so now in order to do so, let me use the same procedure. First of all, let me represent this circuit with other circuit in which the impedances are represented by these blocks. okay, so this is block 1 while this is block 2 here. okay, so let me call it Z1 and this Z2, and here the source current is already known, which is this I, while the values of current, this is I1. Okay, so let me represent it with this red color, or doing it like this is the Z1, while this one is I2. Okay, so let me represent this one with the green color. Okay, and this is Z2. So now we can see that this is a circuit in which this is Z1 while this is Z2. So what we have to do in order to find the value of I1, I have seen that the value of I1 is basically equal to what? Okay, so let me write the formula. The value of I1 according to the current divider law is Z2 divided by Z1 plus Z2 multiplied by I, and this formula is only applicable if Z1 and Z2 are in parallel with each other. Okay, so again I don't know the value of Z1 and Z2 while the value of I is already known, and that is here. Okay, so here let me write their values. So in order to do so, let me first calculate the values of Z1 and Z2. So the value of Z1 is how much? We can see here that this is the inductive reactance, so therefore this is JXL. Okay, so now writing its value, what I will get here J4 ohm. Okay, so that is the value of Z1. In order to find the value of Z2, we can see that here the resistor and the capacitive reactance are connected in series with each other. So therefore what I have to do, this will be R, and here I will have this X of C. So as these are connected in series, so therefore minus J will be added with this X of C, and here I have this Z2. So now putting their values, what I will get, so Z2 is equal to 12 minus J6. Okay, so that is basically the value of Z2. Now in order to find the value of I1, what I have to do, let me put their values here. So the value of Z2 is 12 minus J6 dividing it over Z1 plus Z2. So the value of Z1 is already known, that is J4, while the value of Z2 is plus 12 minus J6. Okay, and multiply it with what? I have to multiply it with this 6 and 30 degrees because of this value. Okay, so this value is already known, which is the source current. So let me solve it now. So in order to solve it, what I have to do, so this is now I1. So I1 is 12 minus J6 divided by, as these two, we can see that this one and this one, these are two the imaginary quantities while this one is the real one. So imaginary quantities will be added together. So therefore here I will get 12 and plus J4 and minus J6 is equal to minus J2. Okay, multiply it with this 6, 30 degrees. Okay, so now again the operations involved here are basically the multiplication and division. So therefore for multiplication and division, again the polar form is the feasible one. So converting these rectangular forms into the polar form, what I have to do, so let me represent them here. So 12 and minus 6 with an iota. So this one is here, and representing it in the polar form, what I have to do, shift 2, okay, 3. So what I will get here 13.4. okay, so 13.4 with an angle of minus 26.5. so 13.4 with an angle of minus 26.56. okay, and dividing over this 12 minus J2, again this is the rectangular form. So let me convert it into the polar form. So this will be 12 minus 2 with an iota. So here this is 12 minus iota, again converting into the polar form, what I will get 12.17. so 12.17, and the angle with it is minus 9.46. okay, so angle with it is minus 9.46. 46 and multiplying it with 6 and 30 degrees. Okay. Similarly, in order to solve it now, multiplying the amplitude, so 13.4 multiplied by 6 divided by 12.17, and the angles here are minus 26.56. okay, and this one is the positive, so adding it with the numerator term here, so these two are the numerators which are added together, while this one is the denominator and the sign of it will be changed, so therefore it will be 9.46. okay, so this is I1, so the I1 is now equal to 13.4 multiplied by 6 divided by 12.17. okay, so it would be 6.6 amperes, while the angles it has are minus 26.56 and plus this is 39.46, because 30 and 9.46 are added, so I will get 39.46. so what I will get, okay, so that will be 12.9. so here I will get 12.9 degrees. so this is the value of current I1 which I have found out by using the current divider law. okay, so in this circuit I have found out the value of I1. Now to find out the current I2, what I have to do, I will represent my calculations with this green color. So now in order to do so, what I have to do, the value of I2 is what? This is Z1 divided by Z1 plus Z2. Why Z1? It is basically explained in my previous video, so I will put a link over here so you can basically see what does it mean to write the Z1 in the numerator despite Z2. okay, so now multiplying it with I, the total current, now putting values here, so the value of I2 is now the value of Z1 is how much? Z1 is J4. okay, so the value of it is J4 and in polar form it will be 4 and 90 degrees. okay, while the Z1 plus Z2 was previously converted into the polar form as well. okay, so that is now 12.17 with an angle of minus 9.46. so 12.17 with an angle of minus 9.46. okay, and the total current here is how much? The total current here is 6 and the angle is 30 degrees. so 6 with an angle of 30 degrees. okay, so these are all the values. so now let me solve them here, because all the values here are now in polar form, so it is now very easy for me to solve them by using the multiplication and division. so I2 is now 4 multiplied by 6 divided by 12.17. okay, and the angles here are 90 degrees plus 30 degrees plus 9.46. okay, so what I will get here, so the value of I2 will be equal to, that would be 4 multiplied by 6 divided by 12.17. okay, so this is now 1.97 amperes. okay, while the angles here are 90 plus 30 is how much? That is 120. so 120 plus 9.46 is 129.46 degrees. so that is the value of current I2 which I wanted to find out. okay, so that's it for the part B of my question 34, and I have seen that how easy it is to find the values of the unknown currents if we know the source current and all the impedances which are connected in parallel with each other. okay, so that's it for today, in which we have covered a very basic current divider rule, which is very important for you to understand in order to find the unknown currents. So that's it for today, and I will see you with some more important stuff in our upcoming video. Stay tuned, and if you have any question, please ask me in the comment section. Thank you so much and see you soon.